today. And this was the example we were doing in the last class. And we went over this join query. And then we went over a list of problems. And the last one, again, you can't know how many disk accesses are there because I didn't give you any information regarding how the file is stored on the storage system. So if you don't have any questions, I'm just going to finish off with indexes. So are there any questions? So one of the things I did mention in the last class is that, indexes are really useful, but there is a cost that is attached to indexes, because every time you add, insert, delete, or update the table, you also have to update the index. So there is a cost. So this one keeps moving. So when there's an insert, delete, or an update of table, the corresponding indexes also have to get updated. So therefore, do not just randomly make an index on every attribute. So there are some attributes on which it's useful to make indexes. So useful indexes would be the primary key, like I mentioned, and this is by default, they're built. So it's done by the database system automatically. It's not something that you need to deal with. Then on candidate keys, anything that you're calling unique, it's a good idea to build indexes on those, because a lot of queries might be generated using candidate keys. Then foreign keys are useful because join queries, if you have an index on the foreign key, it's very useful. So another index that's very useful. So I'll give an example. So in my courses, we have your student ID number, but there's also your first name, middle initial, and last name, or first name, last name. And the key in my courses is your student ID. But most of the queries that we type in are using first name and last name. When I look for, go to WebCat, or I go to my Wildcat Success, I don't know your student ID. So what I'm really using is first name, last name. And so even though first name, last name may not be unique, there are not that many matches. They're not that many people around with the same first name, last name. So attributes that are almost a key, such as first name, last name, they are very useful indexes because a lot of queries come using that. So that's an attribute on which it's really useful to build an index. So an attribute that's almost a key. And when I say it's almost a key, means that there are relatively few people who have the same first name, last name. So you have relatively few rows or tuples. Okay, so, and I'll write down the example because I think it's easier to figure this out using the example. First name plus last name. So that's a very useful index. Another index that is useful is if the table is stored physically clustered on that index. Like for example, let's say the employee table is stored clustered on D number, then it's very useful to build an index on D number. So if tuples are clustered on that attribute or and usually if a system administrator is clustering on an attribute that's non-key, that means that there are a lot of queries that are being generated based on that attribute. So like I said, example is D number in employee table. And in my courses, a lot of questions are asked based on the major. So that's a good attribute. So, if you know that my courses is stored by major, then clustered on that, that's a good attribute to build an index on. And again, it's also based, many queries are based around that particular attribute. So these are useful indexes that it's good to build indexes on those attributes. And there are other attributes, like I mentioned, that are, you should avoid. So indexes that are not useful. So, let's say that I ask this attribute, I give a query saying, how many female students are there in the computer science department? And you might think, oh, it's a good idea to build an index on, sex. But that would be a really, really, really bad idea to build an index on sex, because sex, they're just two values, male and female. At least, currently they just have two values, male and female, or maybe at most three values on that. So if you look up the file, pretty much every block, this block will have a few male values, a few female values. So these are going to be there in pretty much the entire file. So even if you do have an index on this attribute, you have to, if someone asks this query, list all the males in computer science or whatever, I would have to upload pretty much the entire file from disk. So what's the point of building an index? So completely useless index. So an attribute with very few values. So it's not a great idea to build an index on that. Another attribute that it would be, kind of, I don't think there's any point in building an index. So that would be actually salary in an employee database. Because the reason is that other than you see things like the highest salary or the lowest salary, people who are out, on the tails of the distribution, things like salary, if you look at the distribution, those are very much normal distributions, that you have a whole bunch, clustered around a certain area, and then you have few on the tails. So when you do any query on salary, typically you'll end up again searching pretty much the entire file. Even if there's an index, you would have to bring up the entire file, because you will find people with all these, low salaries, high salaries, middle salaries, in pretty much every block. So really, there's not much point in, building an index on salary. So I would say attribute, I'll just say salary. It's much easier to understand with the salary. Salary where common salary values and ranges are stored in almost all blocks. And most of the questions are like, who earns between 50,000 and 60,000, something like that. So what's the point if you are going to have to retrieve pretty much, you know, if you're going to have to retrieve the entire file, what's the point of building an index on it? So, so don't build indexes on fields, attributes like that. And another attribute on which it would be kind of silly to build an index on is on the employee table. Let's look at the address field. Rarely do we ask queries such as, list all the people who, live in, so you give a specific address in there. It's unlikely, the whole address. Maybe, people would have queries on towns or counties or stuff like that. But typically on the entire address, people are not giving queries. So, don't build indexes on that. So attribute on which equality or less than, greater than queries rarely asked. So you kind of figure out what are the queries that are most often asked and build indexes on those queries. Build indexes on those type of, the ones that are used commonly in queries. So I'm going to give a few questions and, using the company database and, just see if you can answer them. So I'm going to give queries and I'll just ask you like what indexes would be useful in context of these queries. So again, I'm going to use the company database. So the query that's asked is, given an employee name, so I'm giving the first name and last name. Find the department name. So suppose you're given a query like this, select, so the department name given the employee name. So what are the fields on which you should build the indexes? So I'll give you some choices, make it easier for you. So on employee, suppose, is it good to build one on first name plus last name and on D number? And in the department table, D number, and 4, D name. So what do you think? So what are the attributes on which it would be useful to build an index? So would you think it would be useful to build it on first name and last name? So just answer, anyone. Which ones of these 4 attributes, on which attributes would it be useful to have an index?
DNO.
DNO?
Yeah.
Okay, so you're saying it should be useful to have one on DNO. Any others, or the rest are all okay?
I think first name and last name, and then D number, but not DNO.
Oh, okay. Yes, actually, so you're right, so this one is the correct one, because you are asking, so first I'm giving the first name. So suppose I want John Smith's, I want to list the department name for John Smith. So I'm going to look for John, I'm going to type John Smith. So it's good to have an index for John Smith, because I have to pull up John Smith from the employee data table, because I need to find his department number. I don't have his department number.
Yeah.
So I have to pull up, so it would be good to have this first name plus last name, else I would have to search the entire table, I might in the worst case, to find John Smith. So once I pull up John Smith, I'll find his department number. So there's no point in having anything out here. So this is fine. But now I got the department number. So now in the department table, I need to look for the department number. So therefore, it's good to have the index on department number in the department table. So there's no point in having department name, of course, because that's what I'm looking for. Once I pull up department number, I'll find it. So I hope everyone understood this one. So I'm going to give a few more just so that you have some practice on this. So the next query is, given the social security number, give the names of all projects the employee works on. So again, I'll give you the choices. So the choices are on employee table, I have social security number. On works on, I have ESSN. And on project, I have P number. So which one of these do you think, there could be one or more or none. So which of these do you think would be useful to have an index on? So while you're doing that, I'll just write down the next query. So just think about it.
Are those all primary keys anyway?
So right now it doesn't, I mean, it may or may not be primary keys. If they are primary keys, they automatically have indexes. But for now, let's just see for this particular query. So my question is only for this query. For this query, which ones would it be useful to have index on? So do you think for this query, would it be useful to have an index on employee social security number? Anyone? Do you think that it would be useful to have one?
Well, if it's already given, doesn't seem like it would be useful.
Yeah, you're right. It's already given. I don't even have to look in the employee table at all, because I just really have to look for ESSN in the works on table. I don't need to look for it in the employee table. So in this case, there is absolutely no point in having, for this particular query, there's no point in having an index on the employee. That doesn't speed up the work in any way. But yes, it does speed it up, because you need to look up the employee social security number in works on. So it's very good to have an index there. And similarly, it's very good to have an index in project, because once you get the project number from the works on table, you can now look in the project and for those P numbers. So the first, second, the works on and project attributes are useful. So this next query is exactly the same as this query. I mean, and the only thing is, I'll just copy it instead of writing the whole thing down. Okay, so, but here I'm going to, so instead of social security number, I'm going to say given the first name plus last name, give the names of all projects the employee works on. So let me just 1 second. And here, so here on the employee, I'm going to have so this next query is, I've just changed it slightly. So now instead of the social security number, I'm going to give the first name and last name and give the name of all projects the employee works on. So, I mean, so these two are still useful here, and it's, you know, there's no change for works on and for project. But the thing is, for the employee table, now you've changed it. Now you're asking the first name and last name. So you need to find the social security number out here. So therefore out here, it would be good to have an index on first name and last name, because you need to find the social security number. I don't have, you know, John Smith's social security number. So here it would be good to have an index on, yes, an index on first name and last name. Okay, so do you think you kind of understood how to figure out, I mean, from a query, how to figure out what indexes would be useful or not? And I'll give you one last question on this. I mean, I would give some questions on this on the final. And again, things like this, they're not difficult at all. They're easy, but just don't do it on an autopilot mode, you know, like you just still have to look at it and, you know, maybe spend a few seconds trying to understand what the question's asking. So given a department name, list all employee social security numbers who work in the department. So you're given a department name and you have to list all the employees who work in the department. So again, the choices are going to be, so we have the department table. So, let me just write this in blue. So we have D number, we have D name, and then we have the employee table, and we have social security number, and we have D number. So for this one, just, you know, check off the indexes that would be useful. Okay, I hope everyone's kind of got a chance to do it. Sometimes hard for me to judge sitting here when I already know the answers. How long would it take for you to do it? And so anyway, for D number, so here again, you're given a department name. And so think about it. So you are given the department name, but you have to find the D number because you have to search in the employee table based on D number. So there's absolutely no point in having an index on D number for this query, but having an index on D name would be very useful. And then when you go down to the employee table, you are searching by the D number. You are looking for all the employees in that particular D number. So therefore, you would want to have an index on D number, and then it'll list all the people who are working in that department. So does this make sense? Does anyone have any questions on this part? So, I mean, that's the reason there's really nothing much I could give in an assignment on indexes so much, because all these questions, they're not particularly difficult, but you just need to understand. I just want to make sure that you understand, while indexes are really useful, there is a cost involved. So only build indexes on attributes that are really useful. And in order to do that, I mean, other than the default indexes like the primary key indexes and the candidate keys and foreign keys, there are other indexes that are, if you look at it, just by looking at some of these queries, you can make out that it would be really useful to have an index on first name and last name, because so many queries are usually generated from there. And the same goes for department. A lot of times people, don't know the number of a department, but they know the department name, like computer science and stuff like that. So that's a very useful index to have. Again, projects, people may not know project numbers, but they know project names. So it's very useful to have indexes on things like that. So there are attributes that do not have, they're not keys or even candidate keys, but it's really useful to have. That's what, because it's human beings who are doing a lot of queries on the computer system. So you try to figure out what are the things that we ask, what are the kind of queries we do. So that's it on indexes. Does anyone have anything? Okay, so then I'm going to come down to what is really the last topic, which is transactions. Which is really what databases are about, are transactions. First, in the new textbook, this would be, I'm doing chapter 20.1, 20.2, 20.3, and 20.6. And if you have the old edition, it's going to be chapter 21, actually. So whatever was 20 is just 21. Okay, so we're going to talk about, because that's what we are using databases, everywhere, banks, airlines, universities, companies, everywhere we are using databases and we are running transactions on them. So the question is, what are transactions? So far, I've really never spoken of transactions. I've always said queries and queries and queries, but I've never said the word transaction. So, but when you start realizing, you look at any applications that's built, it's all built around transactions. So what is a transaction? So let's start with an example that we kind of all relate to. So we'll start with a bank, which I think is a very useful example. So just let's say that I do this very often. I transfer money from one account to another account, maybe from my savings account to my checking account, or money market account to savings, or from my account to my husband's account. So I mean, we transfer money all the time. So let's say I'm doing this. So I have a query. So I'm saying Q1 refers to a query. I'm saying update accounts. So I'm updating my accounts table. Set balance is equal to balance plus 100, where account number is equal to 450. And I run a second transaction, a query. So I'm going to say query 2 is update accounts. I'm updating the accounts table. I'm now setting balance is equal to balance. I'm transferring money from the account number 450 to account number 500, let's say. Okay, so I have done these two queries, but that's the whole idea, is that when I do these two queries, you understand that both these queries must happen. I cannot have, query 1 happening and query 2 not happening, or I cannot have query 2 happening and query 1 not happening, because then the amount of money, let's say that I'm starting with 200, initially, let's say I have $100, $200 in 450, account 450, and I have, $300 in the other account. At the end of this, the sum of the total should remain the same. Nothing should be changed. So you really want that Q1 and Q2 must either both of them must happen or none of them must happen. So what I'm looking for is that Q1, Q2 must be done atomically. So as a single unit. Or it's, it would be like saying all or none. Either both happen or neither happens, but I don't want one to happen and the other not to happen. So both these queries have to be treated as a unit. So that's the thing that we need. And so if you notice so far, what I've been doing in class, so without really explicitly saying anything, is that we have thought that there's only a single user on the database. And we have also thought of that there's a single, that the whole database is stored, say, on your hard disk, so it's a single storage unit, and that there are no failures. But the reality is that there are multiple users of a database, and all of them are running queries concurrently. So another thing is that very often when you're working with banks and airlines and all, their databases are not really stored. Maybe, sometimes they're all stored in one place, but sometimes these databases are stored across data centers. They may not all be in one location. So there is distributed storage. And failures are a fact of life. Failures are happening all the time. That's the thing about distributed, it's happening all the time. So that's where, so how do we ensure that all of these things happen when you have multiple users running things concurrently, when things are failing? How do you ensure something like this? How do you ensure that, Q1 and Q2 and all, they happen and they'll happen as a single unit? So let me give you another example that's very common, which is an airline example. So this was example 1, and this is example 2. So let's say that I'm going to show 2 users who are both trying to book a seat on an airline. So one seat that's available on an airlines. So we have the following queries. We have query Q, which is checking seat availability on the flight. And then you have a query, let's call this query Q0, Q1, which is reserve seat on flight to a passenger. So, and then you have, so this is the flight table. So we're going to update this table flight. And then we're going to assign the seat to the passenger on the reservation table. So there are 2 tables, let's say flight and reservation. And so this is something we do very commonly. We, check whether, check on the flight, whether there's seats available. And then eventually we'll check on the seat and say, okay, I'm going to reserve this one. And then, so that will get updated on the flight table. And also you have to put it in the reservation. You have to enter all the passengers' information on this. So let's see, suppose that there are two users. So let's take a look at what's happening with the two users. I'm going to show the timeline. So this is showing time. And this is user 1. And this is user 2. Okay, so let's say John and Mary are both trying. That's user 1 is John. Maybe that's better. I'll just call them John and Mary. Okay, so John starts up first, and so he's going to check and see. So he's going to do, so he does query Q0. Okay, and then he says, okay, seats available. I'm going to, one. So this guy is looking at seat 10B. And then he says, okay, it's available. So he's going to put that, on the flight table. He's going to make, so you are assigning 10B is going to John. And then we have query Q2. Is a reservation table. Again, you're going to say 10B is going to John on that table. Okay, so that's happening with John. So now let's take a look and see what's happening with Mary now. So we have, so Mary comes up and she does a search out here. So that's Q0. And it's the same thing. She finds that seat 10B is available because at this point in physical time, 10B has not been assigned. So she says, oh, great, 10B is available. So she decides I'm going to take that. So Q1. So she's doing on the flight. She's saying 10B going to Mary. Okay, so she's put down Mary on the flight 10B. And let's say that she does this Q2 is happening out here. So reservation is 10B going to Mary. So now you can see what's happening. So I'm showing you the real timeline out here. So at the end of this, what's going to happen now, if you look out here, in the latest time, flight is going to show John because John's happened in physical time. It happened after Mary's. So you're going to have in the flight table. So flight is going to show 10B being assigned to John. But the reservation table is going to give all details about Mary. Because hers was the last one that ran through. So obviously, you don't really want something like this to happen. So this is an issue. You definitely want that flight and reservation should show the same thing. So at the very, you do want that at least queries Q1 and Q2 are done atomically. So that's what a transaction is. A transaction is a group of queries that must be performed as a unit. They have to happen. So at least, forget Q0 is not such a big deal out here, but you definitely want, that, Q1 and Q2 must, be done atomically. So that's what a transaction is. So let me write down the definition of a transaction. So this is number 1 is that a transaction by the way, it's a short form. I'm going to call a transaction as TX. Okay, so a transaction is a group of queries that must be performed as a unit. Oh, sorry. In order to. So we do want that if you have a timeline like this, so if you have, so we have Q1 and Q2. So they must be performed in order. Q1 must happen and then Q2 must happen, but they must also be performed as a unit. And out here, what's happened out here is that they're not performed as a unit, and I must say atomically. That word is very important. I should have put it in there. So you do not want something else to get in the middle of this, which is what's happened out here. You have Q1 and then someone else did Q1. So it's not going together as a unit, as a one entity. So that must really happen. It must be performed as a unit and it must be performed in order. So, so that is what a transaction is. And there's a little more to a transaction. So let me write the rest of it. And for the next one, I'm again going to do I'll do the bank example. I'm going to revisit the bank example. So that's number one. So and I'll revisit and you can also revisit, and we'll revisit the example 2 also, the airline example. So when you look at the airline example, what's really happened is that, Q1 and Q2 are being performed in order. But the thing is that, there is somebody else's query also interleaved in the middle of this query. So if you look out here, you have Q1 out here. Oh, sorry. Q1 happened. So Q1 happened out here first. And then you have someone else do Q1 out here first. So before this Q2 happened, somebody else jumped in and did Q1. So, and Q1 happened and the file got updated. So that's something else. So, is that even if it's performed in order, you also want to also make sure that other queries don't get in the middle of this particular query. I'm not saying this so well. So I'm going to give another example. I'm going back to bank example. So example 1 revisited. So I'm going back to the bank example. And here I just want to write a little more on the bank example. And instead of writing update, and because it's just too painful, it takes up too much space for me to write down update account, set balance. I'm just going to do it in short form. So let's say that, again, I have these two accounts, X and Y, let's call it. So I have balance. Okay, so I have, so I have bank balance 1 and bank balance 2. Let me just call it balance 1 is equal to 100 and balance 2, let's start up with, is equal to 50. Okay, so I have two bank accounts. Balance 1 is 100 and balance 2 is 50. So, so user 1, or I'll call it balance A, and balance B. So user 1, so transfers money from account A to account B. Okay, so we have two users, user 1 and user 2. So let's say user 1 does the following queries. Q1 is equal to balance A is equal to balance A minus, let's say 10, and query 2 is balance B is equal to balance B plus 10. Okay, so I'm transferring money from A to B, and so the balance has gone by reduced by 10 in one and increased by 10 in the other one. So then this is user 1, and then you have user 2. It runs the following queries. So user 2 is Q1. So essentially user 2 just wants to print the bank balances, but let me just put it down. So user 1 reads, say X is equal to balance A, then he does query B. So read Y is equal to balance B, and then Q3 print both the balances. So print X and Y. Okay, so essentially what I'm saying is that, let's say that, see, my husband and I are, I'm user 1 and I'm transferring a balance of 10 from my account to his account. And let's say user 2 is my husband and he's printing out the balances. So those are the two things that are happening. So we have two transactions. So we have transaction T1. So we have, I'm calling it TX, okay? Transaction T1 is Q1 and Q2, and transaction T2 is Q1, Q2, and Q3. Okay, so what are the legal results when user 2 prints out? So when you're printing out the balances, so you can, altogether there's $150. So either, these are the only two possibilities you should have. Either, either he should get 100 in balance A. So either you should have X is equal to 100 and Y is equal to 50, or user 2 prints out Q3 should get X is equal to 90 and Y is equal to 60. So does that clear to everyone? Like, you shouldn't be seeing something where $10 is higher or $10 is lower than that. The sum total should still be $150, whichever way you do it. I mean, that is the legal way this should happen. Anything else must be wrong. You want to guarantee, whatever database system you're using, you want to guarantee that this balance never, is never changed. When you're using an airline reservation, you should never happen that two people are assigned to the same seat. That should never happen. Those are all things that are wrong. When we check bank balances, it should always be the same. Someone's account should not go up and someone's account should not, the total should always remain the same. If you're transferring between two accounts, one place should increment and the other place should decrement in the similar manner. So that is what it thinks, is that what are the legal results for Q3? They should always be this. So, so this is very important, that in the output, the output must always be either T1 happen first followed by T2. That's what it means. So, or T2 done first followed by T1. So what I'm saying is that if you actually look from a physical time, if you're looking like this, it should always look like either T1 happened first and then T2 happened in time, or you should have T2 happen first followed by T1. You should never have any other result. Anything else would be wrong. If you got a result where you got X is equal to 90 and y is equal to 50, that's wrong. If you got a result that x is equal to 100 and y is equal to 60, that's wrong. So that's what we're going to talk about. How do databases ensure this? So I'll continue with this in the next class. Are there any questions?